So now we're moving on to our next presenter. Dr. Bunning talked, if you looked in one of his slides, he listed our national labs. And in today's symposium, we have two national labs that we're going to hear from. The first one is the Oakridge National Lab with Tom Kurfess. And we at UAMI, since Utah is so focused on composites and carbon fiber and advanced materials and new materials, have worked with Oakridge Labs in their composite program. So we do feel an alignment with the Oakridge Labs. So I'm pleased to bring on Dr. Kurfess, who is he's currently the Chief Manufacturing Officer at Oakridge National Labs, and he's going to share his own slides. Again, his bio is on the, let's stop sharing. His bio is on the website as part of the agenda. You can click on his bio and learn out more about him. And with that, I will turn it over to you, Dr. Kurfess.
Well, thank you very much. I appreciate the introduction. So again, I'm Tom Kurfess, Chief Manufacturing Officer here at Oakridge National Laboratory in Oakridge, Tennessee, just outside of Knoxville. And I'm going to be talking about the democratization of advanced manufacturing. And so the idea really is how do we get the latest technologies out there, and not just to the primes, but really to all of the suppliers, the tier 1, 2, 3, 4, 5 suppliers that are out there, even the mom and pop shops that really make up the backbone of U.S. manufacturing. And so I'm going to do that, and I'm going to leverage some of our work that we're doing in the hybrid area, which is a combination of additive and subtractive. So first thing I want to do is thank a number of my colleagues, the good doctors Feldhausen, Salibi, and Paki. We have we have about 5,500 technical people here at Oakridge National Laboratory, and it's a great place to be. Hopefully we see a light coming at the end of this tunnel. If there's an interest in particular in visiting the manufacturing demonstration facility, which is one of my facilities, you are more than welcome to come out and visit us. It's a very nice place to visit. And also thank you to Department of Energy for funding a good chunk of this work. As I said, I head up the Manufacturing Science Division. Our unofficial mantra is innovating faster than the competition can copy. And really what that means is, look, let's take the latest technology and get it out there into production. And let's get the latest designs and start to produce them. And we'll use all sorts of different capabilities. We'll be talking about digital. But we have some of the large-scale printers. You can go look up the 3D printed car. You'll see actually former President Obama and then Vice President Biden visiting us, taking a look at the car and so forth. But we do have things like metal powder bed. I'll be focusing on hybrid machining and even next generation production systems. This is Medusa. You'll see this in operation momentarily at the end of my talk. These are 3 robots that have big welders on them that are putting down metal onto this rotary table over here, so building large-scale cylindrical type parts. Our vision is rapid innovation, ensuring U.S. dominance in advanced manufacturing, and really our mission is to identify and scale up as well as integrate critical technologies for new and emerging advanced manufacturing sectors. So there's an idea at a low TRL, let's say 1, 2, 3. We're here to help scale it up, and it's not just us on our own. We work with industry partners to scale that technology up, get it into production. I'm talking really more about the digital thread today. And so just to give you a feel for it, it's really about ubiquitous sensing, big data, and AI. If anybody has a kid in high school or even junior high, they're probably programming things like the Arduino over here. This is like $10, maybe $15, $30 for a Raspberry Pi. This system right over here has got way more computing power than what we used to put Neil Armstrong on the moon over 50 years ago. It's basically a Linux system. You program it in Python. And again, typical high school students are programming these. This is another one. This is the particle photon. If you see any of these little scooters, again, I haven't been to a lot of cities recently, but if you see the scooters that are sitting around and so forth, typically driven by a particle photon. They're low cost, pretty much disposable. If you break it, you just go buy a new one, and typically that new one is going to be better than the old one. and in many instances cheaper than the old one, so rapidly upgradable. And then there are just a bunch of sensors out there that we can use. Sensors on the machine, sensors that we can add to the machine and so forth. And really what we look at is how we integrate these sensors together. So back in the old days, we might have a sensor or a machine, and then we'll get some information, we'll send it out to the network. Today, we really use a backbone, a communications backbone, and it might be something like a request and reply, like a REST, which uses hypertext HTTP. And so this is, we just say, hey, machine A, give us some information, and machine A gives us information. Or it might be publish and subscribe, something we might call like an MQTT. And these, again, these are just standard things that are out there. They're used everywhere. Amazon, standard type of usage, Google, et cetera, uses these types of things. And here we might say, hey, machine B, we're going to ask you, we're going to subscribe to your publication, and you're going to be sending information out. And again, that information comes out really in an XML type of file, or more recently JSON, which is just a little bit more of a compact version of XML, but very general purpose. And it really just allows either machine to machine or machine to cloud communication. No static IPs, which really do help you. I'm not going to get too much into the cybersecurity aspects of it, but that is a big one as you plug into these. But these really do help you in terms of cybersecurity. I will throw the cybersecurity issue up. About a third of all cyber attacks in the United States today are targeted on our industry sites. Frankly speaking, they're not really looking at damaging equipment or playing with the process, causing a turbine blade to be misprinted or mismachined. Mostly these attacks really are trying to get intellectual property. So right now, most of the attacks are against these manufacturing areas, trying to get information. We'll talk a little bit about that in a bit. But basically, once we have this going, you can send information up to the cloud. We also might think about the fog. So you've got edge, which is we're computing right here at the machine, right where the sensors are. We have got the cloud. I think people are familiar with that. And then we have fog, where the cloud touches the edge or the ground. And that's kind of a hybrid, if you will, between the edge and cloud. So we would maybe do some processing here. If I need some more power, I can reach out into the cloud. Again, lots of interesting stuff going on there. But once you start to integrate these things, there's our friend. I won't say her name because many of your systems at home might light up. But basically, this allows us, these types of capabilities allow us to go right into it. You get to say, hey, my friend Amazon Echo, what is machine C doing right now? Oh, it's building this part, and here's the runtime and the whole bit. So all of that is easily integrable given this type of architecture and structure. And certainly getting stuff out to a smartphone, again, these can be web-based or a tablet, is relatively easy. So it's very easy access, very low-cost computing, and very low-cost capability. To give you a little bit of a feel, these are just two different types of machines at some of our facilities. This is an Okuma, this is a Mazak. They're both running MT Connect, which is a standard protocol for communication. And in this particular case, we're just getting spindle speed directly off of the machine. And so now I can tell when my machine is running and when it's not. So we can take a look at machine utilization. In this particular case, the company we were doing some work with, they were making just one-off turbine blades, so just a replacement blade. They weren't making hundreds of the same type, and they were interested in how long does it take me to make a particular blade. Well, here's the time. I start my spindle here, and then it stops here. This is how long it takes me to take the blade. And so after about a year's worth of data taking, we could go back and run some statistic. They might have made 10 or 20 of these blades over that 1 year period. And now we can figure out, we can put together your standard control chart, X bar, S charts for this blade and maybe for this blade and so forth. And so relatively straightforward. This costs zero because the information is coming directly off of the machine. And the machine is capable of doing it. You have to connect the machine up to your network. Again, be very careful about connecting it up with cybersecurity issues. Lots of good opportunities to engage on cybersecurity as well. If the machine doesn't have a capability to be connected to the network, or if it doesn't have this the output capability, a very simple sensor like a vibration sensor. So just an accelerometer. Easiest one is probably a triax accelerometer. You could take an accelerometer, connect it to your Wi-Fi. So a Wi-Fi chip, actually accelerometer hooked into an Arduino. That whole package probably costs you $30 or $40. In fact, probably the most expensive part of a package like that would be the box that the electronics package goes into. So The processor, the sensor, the whole bit are cheaper than the box that it goes into to keep it protected in the shop environment. Machine is vibrating, I'm making the part. Machine is not vibrating, I'm done making the part. Now, here's what's really interesting with this is once you have this information, one of the things I looked at is I said, oh, well, here we have the setup time. So this downtime is the setup time for this next blade. I already have all the data. Let's go compute the setup time. If I'm just making 1 or 2 blades at a time, it's going to be the setup time that dominates. So I took a look at it, and I said, wow, the standard deviation of the setup time for this blade is all over the place. It's super big. Why is it so big, for this, for any of the blades? It's really spread out all over the place. And what you learn, and again, it's not a big surprise, but unless you think about it and look at the numbers, you don't think about it. If this blade and this blade are very similar in nature and use a lot of the same tooling, setup time is going to be small. If these blades are very different in nature, I've got to do a lot of tooling changeover. Setup is big. So one of the rules we gave back to this company is we said, look, to reduce your setup time, let's group. And this is something that you would normally do. Again, just didn't think about it. Let's group, we produce the first blade, and then let's pick a second blade so that it's very similar to the first blade. So you group them, group technology, group those blades together. We wound up with a 17% time savings or reduction in idle time on the machine tools. So it was just absolutely fantastic. And by the way, that's just looking at spindle spinning. One of my colleagues, he heads up our machine tool group over here, Scott Smith, he said, look, when he was a grad student 30, 35 years ago, we would spend weeks putting instruments on these machines, and then we would run experiments and analyze all of the data. Today, all of those instruments, all of those sensors are already on the machine. So every time we make a cut in production, we're running an experiment, and we can get information off of our machines. So these are the types of things that we actually look at, and basically the data are free. Now let's take a peek at some hybrid systems. So we're going to go a little bit more advanced. And hybrid is just a combination of additive and subtractive, which would be machining. So again, you're going to print some material out, and then you're going to machine it down to get the right shape. In this particular case, we are printing just this propeller over here. You can see that we've got all sorts of overhangs and so forth. But again, it's a 5-axis machine, so we're printing this while rotating. So in fact, we can, if you will, change the direction of gravity. So this allows us to print something like this propeller. And how we printed this propeller is we just started with a piece of bar stock and then printed the material on there and then machined it to a final shape, but printed without using the support structures. Typically, that's kind of good for these metal type of geometries, or when we're using metal, because again, it's not so easy to break away that support structure. So if we just take a look at hybrid, it's again a combination of CNC machining and additive manufacturing. On the machining side, it's repeatable, precise. We get good service finish, high productivity. But again, a lot of times you're machining away a lot of extra material. We can get rid of that when we're doing additive because we can just print what we would call, like a near net shape form. We call it a preform. We have a lot of geometric freedom there, and we have some pretty cool material options. And I'll give you an example of what we might do with some of the materials in a little bit. But sort of, a key thing here is, and I want to point out, there are some similarities. So I'll give you a little bit of sort of kind of some thoughts on this hybrid machine. The similarities between machining and additive. In machining, we have roughing cycles. And so usually you're hogging out a lot of material. It's lower precision, rougher surface finish in the whole bit. And then we have a finish pass where you have a lower material removal rate, but you get a much higher precision. Same thing in general with additive manufacturing. If I have large material deposition rates, basically I have a much lower accuracy system. So here we're looking at a blown powder system. We have systems, and I'll show them you a little bit, that have laser wire, so laser welders on them, or even MIG welders where we put down 3-inch or 6-inch beads on them. So they're very crude in terms of the geometry, but we can put a lot of material down very fast. But again, these are going to be made of stacking up weld beads together. So these are just the different types of things that we would look at. So if we take a look at some of the hybrid operations, one of the really nice things, in particular, as we start to go to a 4 or 5 axis machine, is we can change the direction of gravity, if you will. You notice that on the propeller, and this is just a simple example where we're printing this L shape over here, and nominally you would need some sort of support below this blue structure, but we printed the blue part first in this orientation and then rotated and printed the green part second. So you can do some very interesting things. In general, for our additive, we're either going to use a blown powder, which is typically about 1/2 pound per hour, but we get some pretty nice resolution there, or the wire feed, which is about an order of magnitude faster, but again, it's a rougher finish. But the beauty of it, I think, if you've used any of the powder systems, you've got to have respirators and special gloves and so forth to deal with the powder. Wire feed, I just go to MSC or to Lincoln Electric, order up my spool of wire and stick it in the machine, and I'm ready to go. So in terms of operations in a shop, this one is very easy to go with, as opposed to anything special going on with the blown powder. Even in terms of post-processing, a lot of times you've got to clean the powder out. Here, no powder to clean out. So again, people say, well, what's going to win? They each have their advantages, so it just depends on. It's like saying what's the best machine tool? Is it a mill? Is it a lathe? Is it vertical? Is it horizontal? They each have their advantages. And then, of course, in subtractive, right now we're just talking your standard machining. In terms of some of the lower costs, and this is a great example we get from a colleague, Professor Yamazaki out at Berkeley. He shows this part that's usually made out of machined Inconel. So I start out with a big Inconel tube, and I machine it all the way to get all these different features. What he has shown here is we start out with a material, 316 stainless substrate, and we just print the Inconel, and then we machine it to final shape. So now you're using much less Inconel, and you're having to machine a lot less Inconel. So 97% material cost reduction and significant reduction in terms of time and so forth. You know, saves you an awful lot of money as well. You know, 90,000 versus 2,500. So not too bad. So let's take a look at both. This is a wire machine. And so this is the Mazak. This is a 5-axis Mazak machine. And again, one of the things you have to be careful about is we have an additive head and a subtractive spindle. So you do lose this distance, actually twice this distance in terms of the machine capability, because the part's got to be able to reach under here and also reach under here. You know, I can't use the full travel of the machine because it can't get to both of these of the deposition and the machining part at the same time. So you do lose some space when you put the when you put the additive head in there. But again, in this particular case, we made this propeller on here, no support structures and so forth, built it up where we didn't build it up from scratch. We started with a piece of bar stock. The other thing that I really do want to point out is people are familiar with constant surface speed on their machining operations. You have the same type of thing in the additive operations. So basically, constant surface speed is constant material removal rate. Here we have a constant material deposition rate. And that is really, we're feeding the wire out at a constant speed. And so what you can see, we're actually putting material down in a ball joint. So this is a ball socket for, I believe it's a hip implant. But you can see when you get to the apex of the sphere, you can see that this actually spins much faster because you've got to get a higher surface speed. Well, you've got to have a constant surface speed as you get to the apex of that sphere. So it's going to spin faster because we're putting down a constant amount of material. So lots of synergies between the two. The blown powder system that we show over here, this is the Okuma one. And what's really nice about this is this actually is more of it's also a mill turn machine. I think we can go up to about 800 RPM. So here you can actually see that we're building this, we'll call it a nose cone, if you will. It could just be a cup or a vase. But as we're building it, we're not going back and forth. We're just spinning it. So this is more of a cylindrical projection, but there is no start and stop here, so we can get continuous motion. And where we need to build the wall up, you can see we're rocking it back and forth to allow us to build it up. So you don't have to worry about the overhang structure there. You build some, you rock it in a little bit, and then you continue to build the thickness in terms of the wall. The other thing that's really cool about this one is here you're actually looking at the weld pool, and we're just starting to work on some controls areas in here, but you're looking down the core of the fiber optics, so we can actually see what's going on with the weld pool, which is really, it's very interesting. Now, there's a lot of, it's not just about the machine as well. We do a lot of work with Hypermill or with Autodesk and so forth. When you think about slicing on the 5-axis machine, so here we built this structure. This is just a hollow structure over here. This was done on the Mazak, but again, you can't slice it linearly. You have to slice it into chord fashion because you're really printing it in this chordal fashion. And when you print it up, and here I'm just showing it on the impeller, you can print it up. Again, no support structures, as you can see, because we're rotating as we're printing it. Now, the one thing I do want to highlight is that as you print this thing, clearly I've got less material that's got to come in over here. I can't just print a straight plane or a straight line over here. So as you can see here, when we blow up this area, we do have to do some modifications. So it's not just, okay, we're going to go off and use this, but we are actually going to do some modifications to your classical approaches. So these types of machines are really allowing us to do a whole lot more with our systems as we move along. But you've got to think a little bit more out of the box. The other thing that's really nice is you could imagine machining this thing. So as we machine this thing, it's going to ring like heck. One of the things that we might do, as opposed for access, for example, it's hard to get a tool in here. We might actually do the machining ahead of time. So print some, then machine, print some more, then machine, so we can use smaller tooling. The other really nice thing about this is as you're machining, you might get some motion as you do some stress relieving, some residual stresses. If you machine here and you've got this very long part, you've got a lot of motion out here. On the other hand, we can machine on a stubby part. It might move a little bit, but then we can put down some more material. So we can work our way out and really avoid some of the motions that we see from some of the residual stresses. So one of the things we're looking at is just blade repair. So here we're actually looking at how do we repair the blade and how do we control that blade repair. I'm not going to get too much into this, but basically we can come in, we can measure, probe in the machine, probe the blade, remove the worn area, print on new material, and then machine. This is just a surrogate blade; it's not an actual blade, and then machine it to merge that material together, so we can actually repair the blade. And we're doing a lot of this work in conjunction with a number of our partners, Delta Tech Ops. Excuse me, Zeiss. Zeiss is doing a lot of our inspection and so forth. And we are using, and this actually is a video, and this is showing the information coming off of the machine. We are using information flowing out of the machine to understand what's going on with our particular part. And as we're making this part, we're actually recording information about what the machine is doing. So in fact, if I go to the next one here, and this is just the record for this particular part here, we understand exactly all of the settings on the machine. And so we can make sure that we're right at our 100%. And here we're taking a look at the feed rate override. So we've been making this part exactly at the design feed. Now, again, if you're thinking, well, on the machining side, a lot of times when people are running it, they might run it a little bit below. So a slower operation because they're afraid of the machining the first time around. This is really a bad thing when we're talking about additive. You really have to hit your target trajectories and velocities for additive to get the right part. And in fact, what you see over here is somebody has said, okay, well, we're machining, we're being a little bit cautious. Okay, now I'm going to crank it up. And I think we've all seen our operators operate at 120, 130, 140%. And so again, when we make a part, we can record all the machine parameters and make sure they're all within specifications. So we know when that part shows up, it'll show up with its digital passport. From a cyber secure perspective, it was made according to spec. This is not a counterfeit. It is original, and it was made according to spec. So we can move this along. The other thing we can do is we can actually control. So now, using our standard machine tool, so this is a hybrid machine tool, but we can actually control it using more advanced capabilities. Certainly we have in-machine probing, but we can also start to take a look at infrared cameras, and I'll show you what we're doing there in just a minute. But the idea really is to say, look, if the part gets too hot, that camera is going to tell an outside computer out in the cloud saying, hey, part is too hot, hold up on the machine. So we're now controlling the machine from the cloud. It's not a real-time, it's a pseudo real-time control. It's on a layer-by-layer basis, but the architecture is completely in place. The machines you buy today are capable of doing this in a secure fashion if you interface them correctly. So let me give you the example here. So in this particular case, we're just building a wall. It's a surrogate for a turbine blade. Here we're just going as fast as we can, just hey, put it down. But you can see that this overheats and it kind of bends over and kind of melts over, and it's really a mess. What you're seeing over here is we're watching it. When the camera says the part is too hot, we're telling the machine to hold on for just a minute. And then when it's ready to make the next layer, when it cools down enough, then it makes the next layer. You can see here initially, of course, we're printing on a cool surface. So we're okay. We actually print fairly rapidly. And then over time, this heat builds up, and so it slows down the printing. And so you can actually see what the temperature looks like, and we make sure it does not go beyond a certain amount. We've actually taken...
Hey, Tom.
Yes.
We're running a little over, and I see you've got 22 total slides. Could we move this along a bit?
Yeah, sure. I was targeting this for a 30-minute presentation, but I could certainly bring...
on time. And we also want to address the issue of how do our research community interact with Oakridge National Labs.
Right. Okay. Well, that I think that's fine. And so, one of the things that we have going on over here is and I'll just show you this last slide. And I don't think that this will probably be good enough in terms of where we really want to go. This last slide here, this last image here, basically what's happening is we're now probing the part. So we're actually taking a look at the part cooling, and so you can see this is just the typical cooling for the part, and we actually see it coming down. And so we know exactly when we're ready to, the stresses are at the right part and so forth, and we can move to the next level in terms of printing. The other thing that we can actually see is we have this information it's stored, so we know about the material characteristics and so forth. So we know that we have the right material, everything is correct in terms of the process. And so really where we're at, in fact, I think probably, probably where I'll go is we'll just go right to the last slide over here. And again, my apologies. I was timed for, and my timer here says we're at about 22 minutes, but no problem in terms of moving it forward. I want to point out a couple of things. So a lot of what we're talking about, people say, well, I'm going to lose my job because of automation. This is not true. What we are doing here, you still need an operator, you still need people in there. You are making life better. I testified in front of Congress. This was about 10 years ago. Congressman said, when am I going to get the robot to unload the dishwasher? The computer scientist next to me said, in about 10 years, we're still not that close. This is thousands, tens of thousands of dollars. This is a few $100s. They're not compatible, right? The person is still way better. People are excellent, and so they work together. So there also are the workforce development, but making sure that we integrate it into the workforce. So look, so here's my friend Medusa. So here are my 3 robots. They're working synchronously here together. Here they're working independently on the large turntable. But basically where we're at is, look, the digital thread is a two-way street. So how you're going to be working with this is data are going to be coming up. We're going to be analyzing processes, but we're also going to be supporting the workforce that's out there. In terms of working with us, really what happens is we're about identifying new technology. So if there's a new technology that you want to get out there, we're not going to do it on our own. We partner with industry. So you saw the Mazak machine. This is a Lincoln electric setup in terms of welding. So what we do, and we typically operate in a creative fashion. So in this particular case, Lincoln is putting in a certain amount of money, and the Department of Energy is matching it. The Department of Energy is funding us to do a lot of the work with Lincoln on this system. They bring in, I would say, about 80% of the technical know-how and capability for this project. We bring in about 20% of the materials and the control and the process modeling capability that really pushes us over the finish line. Really what we're about is we can de-risk the type of work that's going on. So companies will say, this is too much for us to take on. We partner with the companies, and that partnering can be bring in equipment. We'll use your equipment. We don't even want to own your equipment. We'll give it back to you in the end, but we can work on the depreciation schedule for that equipment. We have engineers from our partners. We have technicians from our partners in here working on this. And by the way, they're leveraging it. So for example, Zeiss is another partner. You saw that. So we'll print something on this system, and then we'll inspect it on our Zeiss tomography machines. It's good for Lincoln. It's good for Zeiss. It's good for everybody. So again, the idea is to scale technology as quickly as possible. We can do this in an open environment like the manufacturing demonstration facility. We can do it in an ITAR controlled space like our carbon fiber technology facility, or we can do it in a classified facility in the SCIF. And our whole approach is try and do it as much in the open as possible to try and keep our cost levels down. So again, the idea really is there's technology that is out there that you could use that's important to U.S. industry, whether again on the civilian side, or on the military side, important to U.S. industry that we scale it up. We're the place that you come to work on it. Now it's got to fit within our portfolio. I encourage you to go to our website. So all you have to do is look up Oakridge National Laboratory and Manufacturing Demonstration Facility, or Oakridge National Laboratory and Manufacturing. You'll see everything that's going on over here. If it fits in the portfolio, feel free to ping us. We've got a whole team that are working with individuals. We're not super concerned about intellectual property. We don't want the intellectual property. We want to give it to our partners. So those terms are very open. They're very generous. You got to pay a little bit because that's what the law says, but we're really not out, we're not trying to make funding ourselves and so forth, along those intellectual property lines. Anyways, I'll close with one of my favorite statements from one of my favorite 20th century philosophers, and it was certainly true in the 20th century, and it's very true today. In times of change, learners inherit the earth, while learners learned find themselves beautifully equipped to deal with a world that no longer exists. And that comes from Eric Hoffer. And the reality is technology is accelerating really quickly, and we are here to help that technology acceleration to get it into mainstream production. Thanks very much. Be very happy to answer any questions.
That was fantastic. So how does a research organization interact with INL?
Well, we're Oakridge National Laboratories, but I got to tell you, that's okay. Idaho National Laboratory is one of our partners, and so in fact, they may interact via our operations with Idaho National Laboratory, in particular on the cybersecurity side. But basically, how we interact. I mean, just this morning, so Mazak, you saw that machine. We were sitting with their overall engineering and design team and taking a look at what do the next generation systems need to look like. And then we'll design it and we'll build it. And in fact, that next generation system is here. We'll even run, trial parts for potential customers and so forth. So again, we don't own that particular piece of equipment. So in fact, once we're done with it and we move on to the next project, maybe that customer will buy it right off of our floor and take it. So the idea is really working together and getting things moving. If you come out and visit, if you come in another 3 or 4 years, you will not see the same equipment on our floor because we are always moving into next generation technology.
So you're really commercializing the technology and then moving it out of the lab.
Well, we're working with our commercial partners, but we're making it commercially viable. So it's not just, yep, we're working on the technology, but what's the value proposition? What's the business proposition? So again, the hybrid machine, the beauty of it is, look, do you have enough business to justify this big 3D printer? Probably not initially, but look, it's also a machine tool. So you can use it as a 5-axis machine tool. Maybe you're only using it 10% of the time for additive, but while you build up that business, you can still use it as a machine tool. So, we start to take a look at a lot of the techno-economic analysis that's out there.
Well, thank you so much. Great presentation. Appreciate it. And I'm going to take you up on it. I'm going to come out and see your labs out there at Oakridge National Labs. Thank you.
So Linda, I know we're running a bit behind. We do have a question. Someone's raised their hand. Lee?
Okay.
Sure. Or Leah?
Okay, yeah. Tom, this is Andre Lee from Michigan State University. Beautiful talk.
Thank you.
How do you guys, I've seen some of these additive manufacturing that tend to be what I refer to as the traditional materials. Sort of metals or powders or ceramics and polymer powders. But when we start dealing with composite, where that you have a continuous fiber, and how do you guys, any thought about in the sort of a manufacturing world that from your end, from an additive perspective, for continuous fiber reinforced composite as a reinforcement material system?
Yeah. So you saw the picture of the Cobra, the 3D printed car. There were actually we do have the capability, and these are on our BAMs, our big area additive manufacturing polymer, of putting down a continuous fiber strand into the feed. So we actually these are the input are pellets. So these are our extruders with augers and so forth on them. One of the other things that we have learned is you don't need the continuous fiber. I think. And pardon my English here, but I believe it's if you get to about 3 inches long, you do get the same benefits of the continuous fiber. But yes, on the polymer side, we can't extrude the continuous fiber. We do have extrusion systems, again, polymer in our machine tools, but we haven't gone that far in the machine tool. So I think that there's a very good possibility there. Yep.
Thank you.
Yep.
Again, thank you very much. I'm sorry, we do have to move on.